Welcome back to Daily Dose of Space. For most of the 20th century, scientists believed they understood the future of the universe. Not in detail, but in direction. Gravity pulls things together. Matter attracts matter. Over enough time, expansion should slow down. The universe, they thought, was like a stone thrown upward, still moving, but destined to lose speed. That belief was so deeply ingrained that no one seriously questioned it, until the universe itself quietly proved everyone wrong. A universe that made sense. For decades, cosmology rested on a simple assumption. The universe began with the Big Bang and has been expanding ever since. Galaxies move away from each other because Shanging itself is stretching. That much was clear. What mattered was the rate. Gravity produced by all matter in the universe should act like a brake. The more matter there is, the stronger the slowdown. Even if the universe never collapses, its expansion should at least be decelerating. This idea felt intuitive. It matched everyday experience. It matched equations. It matched expectations. Entire models of the universe were built around one question: how fast is expansion slowing down? No one expected the answer to be, it isn't. Looking back in time. To measure cosmic expansion, astronomers needed distance markers, objects so bright and predictable that their true luminosity could be known, even billions of light years away. They found them in a specific kind of exploding star, Type 1a supernovae. These explosions occur when a white dwarf star reaches a critical mass and detonates. The physics is consistent. The brightness is reliable. By comparing how bright these explosions appear to how bright they should be, astronomers can calculate distance. By measuring how much their light is stretched, they can calculate how fast the universe was expanding when that light was emitted. In the 1990s, two independent teams began using these supernovae to map the universe's expansion history. They expected to measure deceleration. Instead, they found something profoundly disturbing. The result? The supernovae were too faint. At first, this seemed like an error. Dust could dim the light. Instruments could be miscalibrated. The data could be biased. Every mundane explanation was explored, tested, and retested. But the result refused to go away. Distant supernovae were farther away than they should be if expansion were slowing down. The only explanation that fit the data was deeply counterintuitive. The expansion of the universe was speeding up. Not in the past, not temporarily. Right now. This was not just unexpected. It directly contradicted the most basic assumptions about how gravity should shape the cosmos. A force with no name. If expansion is accelerating, something must be overpowering gravity on the largest scales. Something pushing space apart. But no known force could do this. To make the equations work, cosmologists resurrected an old idea originally introduced by Einstein and later abandoned: a constant energy built into space itself. A form of energy that does not dilute as the universe expands. They called it dark energy, not because it is evil or mysterious by nature, but because it cannot be seen, touched, or directly measured. Its presence is inferred only through its effect on cosmic expansion. Dark energy does not clump like matter. It does not form structures. It simply exists everywhere, quietly accelerating the universe, and it dominates everything. The numbers that changed reality. The most shocking realization came next. When scientists calculated how much dark energy must exist to cause the observed acceleration, the answer was staggering. About 70% of the universe. Normal matter, everything we see, touch, and are made of accounts for less than 5%. Dark matter adds another chunk. But dark energy outweighs them all combined. This means that most of reality is governed by something we do not understand. Galaxies, stars, planets, life itself, all of it exists in a universe whose behavior is dictated by an invisible component with no clear physical explanation. This was not a small correction to cosmology. It was a complete rewrite. A universe with a very strange future. Once acceleration was accepted, the future of the universe had to be reimagined. If dark energy remains constant, expansion will continue forever. Galaxies will drift beyond each other's reach. The night sky will grow emptier. Eventually, distant galaxies will disappear entirely from view. If dark energy grows stronger, the outcome is even more extreme. Space itself could eventually tear apart galaxies, stars, planets, and even atoms. This scenario is called the Big Rip, and while it remains speculative, it is mathematically allowed. For the first time, the ultimate fate of everything depended on a force no one could explain. Why this discovery hurt? Once acceleration was accepted, the future of the universe had to be reimagined. If dark energy remains constant, expansion will continue forever. Galaxies will drift beyond each other's reach. The night sky will grow emptier. Eventually, distant galaxies will disappear entirely from view. If dark energy grows stronger, the outcome is even more extreme. Space itself could eventually tear apart galaxies, stars, planets, and even atoms. This scenario is called the Big Rip, and while it remains speculative, it is mathematically allowed. For the first time, the ultimate fate of everything depended on a force no one could explain. The universe that refused simplicity. What makes this discovery truly transformative is not just acceleration itself, but what it says about our assumptions. The universe is not obligated to behave intuitively. It is not obligated to be simple, and it is certainly not obligated to fit within the frameworks we prefer. For centuries, progress came from refining existing ideas. Dark energy forced scientists to admit that refinement was not enough. Something entirely new may be required. New physics, new concepts, new ways of thinking about space, time, and reality itself. Living inside the unknown. Today, dark energy remains one of the greatest mysteries in science. Entire missions are dedicated to measuring its behavior more precisely, not to understand it fully, but simply to constrain how little we know. We live in a universe that is accelerating away from itself, driven by something invisible, silent, and dominant. And the most unsettling part is this: the universe did not announce this discovery loudly. It revealed it quietly, through faint points of light at the edge of visibility. A discovery that forced scientists to rethink everything did not arrive as a revolution. It arrived as a discrepancy.